Hello, Dan here from howtomechatronics.com, and in this video we will learn how to build a CNC machine with a step-by-step guide so you can easily build one on your own. This is a fully 3D printed CNC machine or a CNC router that I designed with two specific goals in mind: to be as rigid as possible and to be as simple as possible to build. Being rigid directly affects the performance of the machine, and besides engraving and cutting wood, I wanted this CNC router to be capable of engraving and cutting aluminum. It turned out it can do that quite confidently. Here's how it looks ripping through aluminum with 4mm depth of cut, 1.2mm width of cut at 1200mm per minute feed rate. And here's an example of machining a propeller out of aluminum. With just a little bit of sanding, the propeller surface turned out super smooth. I also did some accuracy tests by cutting various shapes out of aluminum. If we use appropriate fits and speeds, we can get the aluminum parts within 0.06mm accuracy. I think that's a pretty decent accuracy, considering it's a 3D printed CNC machine, using a trimmer router and an Arduino Uno and Gerbil for the motion control. Engraving aluminum is a breeze. I did few keychains engravings with very small details under 1mm and they came out great. I also tried engraving brass, which also turned out great. This 3D printed CNC router is even capable of cutting steel. My second goal for this CNC machine was to be as simple as possible to build, which meant that I didn't want to use any power tool for making the machine. No cutting aluminum extrusions with a saw, no drilling, no tapping, nothing. Literally, you can build this CNC machine with just a set of Allen keys, because I specifically designed it to utilize just standard components that can be easily sourced from sites like Amazon, AliExpress or any other store of your choice. So it's almost like a DIY kit that you just have to assemble it. Though there is a caveat, of course you need a 3D printer in order to make this CNC machine. But I don't think it's a big of a deal, as even if you don't have one, nowadays there are so many 3D printing services from where we can easily get the 3D printed parts for it. I'm calling this CNC machine a fully 3D printed CNC machine, as the entire CNC structure is based on 3D printed parts, including the X and the Z axis plates, the router mount, and even the ball screw bearing blocks are 3D printed. The design was optimized to get the most out of the fact that we can easily print complex parts with a 3D printer. In combination with some 20 by 40mm aluminum extrusions, 15mm linear rails and 16mm ball screws, I think I managed to get a decent performance out of it. It's capable of engraving and cutting precision parts out of aluminum, and the wood projects are a breeze. It can easily cut any hardwood. And the wood engravings are just perfect. Just take a look at this 340 by 340 3D relief in beech hardwood. It looks stunning. The work area is 450 by 350 by 110mm, but the coolest part is that we can easily scale this CNC machine. We can simply use longer components for some of the aluminum extrusions, the linear rails and the ball screws, and we instantly get larger work area, while all other components and the assembly process itself remain the same. I will include details about which components define the work area of the machine, so you can get your desired work area by choosing the right components. As always, you can find these details, together with the complete list of all components needed for this CNC machine, or the bill of materials, on the website article, as well as the 3D model and the STL files needed for 3D printing the parts. Nevertheless, now let me walk you through the entire process of building this CNC machine, starting from the design, 3D printing, assembling and making the electronics control box, to programming the microcontroller and doing your first cuts with it. I designed this CNC machine using Onshape, which is also the sponsor of this video. Onshape is the world's most widely used cloud-native CAD and PDM platform. It runs on any device, anywhere, requiring zero IT. Companies like Trek, Garmin and Boom Supersonic have moved their design teams to Onshape. They were fed up with errors, time waste and hidden costs of outdated file-based CAD and PDM. Unlike traditional systems like SolidWorks, only Onshape eliminates crashes and never loses data, enables secure real-time collaboration, tracks all activities and provides infinite restore, and has a built-in PDM with branching and merging. Onshape is 100% cloud native, so no installs, no downloads. It runs entirely on your browser or on the mobile app. You just have to log in and start working. No hardware maintenance required. All the heavy computation, like complex features and large assemblies, happens on the Onshape's servers, not on your computer. This means you can run full professional grade CAD on a basic Chromebook, a Mac or a Linux machine or a tablet. I particularly like this feature as it enables me to work on my designs anywhere and on anything. And it's not just CAD, Onshape also features simulation, rendering, CAM and more. I actually used the Onshape CAM Studio to make the aluminum propeller with this CNC machine. If you are an engineer, definitely check out Onshape. You can get up to 6 months of the Pro version free through my link in the description. Now let me show you how I came up with this CNC machine design. My first input parameters for the design was that I wanted to use aluminum extrusions for the CNC frame, but with standard dimensions which can be easily sourced, so we don't have to cut them to size. The length of these aluminum extrusions is usually offered with 100 mm increments. So that's why I chose to use 600 mm long extrusions for the base and 700, 200 and 100 mm long extrusions for the gantry. This constrains a lot the design of the rest of the parts, but luckily we will be using a 3D printer, which enables us to make more complex parts. Take a look at this bracket for example, which connects the gantry to the linear rail blocks. Nobody would ever machine such a part out of aluminum, let's say, because it has way too complex shape and it's not reasonable to make it at all. But with a 3D printer, we can easily get that part. So I used this ability that we have with 3D printers to print complex parts to tackle the constraint that I had for only using extrusions available with lengths with 100 mm increments. And of course, as the priority when designing a CNC machine is always to make it as rigid as possible, I probably went a little wild with this bracket design, but I wanted to secure it on both the sides and the top extrusions, so that it transferred the motion and the forces from the gantry to the linear rail blocks with the least deflection. All other parts were designed with the same philosophy. I even decided to have the ball screw bearing blocks and the ball nut mounting block made with a 3D printer, because using their suitable standard bearing and ball nut mounting block would have constrained the design and the placement of the parts onto the aluminum extrusions with their fixed mounting holes. The X and the Z axis plate are also fully 3D printed, as well as the router mount. I integrated the ball screw nut mounts into the plates themselves in order to keep the distance from the router end mill to the gantry as small as possible, and so keep the forces and the moments lower and ultimately have lower deflection. You can find the 3D model of this CNC router or the link to this Onshape project where you can copy and edit this project, as well as the STL files needed for 3D printing the parts on the website article. The link is in the description of the video. I used the Creality K2 Pro 3D printer for printing all of the parts. In order to get accurate 3D printed parts, we should use the horizontal and whole horizontal expansion features, or in the Creality slicer, they are called XY contour and hole compensation. I used a value of 0.05 mm for the hole compensation in order to get a tight fit of the bolts with the 3D printed parts. I also made the holes around 0.1 mm smaller in order to have better fit. For example, for the M5 bolts, I made the holes diameters 4.9 mm, or for the M4 bolts, I made the holes diameter 3.92 mm. In that way, we cannot just pass the bolt through that hole of the 3D printed part, but instead we have to screw the bolt through that hole. The bolt thread will have to make a thread into the 3D printed part, and in that way we are like reinforcing the 3D printed part, thus making it stronger. Though we should be careful, as if we make the fit too tight, we won't be able to overcome the newly created thread in the 3D printed part, and we won't be able to tighten the nut on the other side. So that's why you should do some test prints to see how your 3D printer is making the holes and adjust them with the horizontal expansion or XY hole compensation feature in the slicing software appropriately. As this CNC build is entirely based on 3D printed parts, there is one more important thing to discuss that affects the strength of the 3D printed parts, and that's the printing orientation. The stiffness or the bending modulus of the part is much higher in the XY plate, as in that way the forces act against the continuous strength of the extruded material, whereas the bending modulus in the Z-axis is lower because it depends on the bonding between the layers. Here I 3D printed the same part in two different orientations in order to test and see how much of a difference it makes in real life example. Using a dial indicator, I'm measuring how much the part will deflect or bend under a load. The one printed in the orientation where the forces act on the Z-axis showed a deflection of around 0.08 mm at a force of around 72 newtons. On the other hand, the printed part in the orientation where the main force acts against the XY plate showed the same deflection of 0.08 mm at a force of around 82 newtons. So that's around 12% difference, and it proves that the printing orientation really does affect the strength and the stiffness of the part. And one more thing that affects the strength of the part, of course, is the material choice. This part was printed with carbon fiber PLA, and if we compare it to a normal PLA, it showed a difference of around 15% in stiffness. The PLA part deflected 0.08 mm at around 69 newtons, whereas the carbon fiber PLA part at around 82 newtons of force, with the same XY plate print orientation. I also did several more tests with some 10 by 10 mm bars and got similar results. The carbon fiber PLA bars with the XY print orientation were the strongest or the stiffest. So that's why I decided to use carbon fiber PLA for this CNC machine build in order to get the maximum rigidity. Though for printing carbon fiber PLA we need a 3D printer capable of doing that with hardened steel nozzle that can handle abrasive materials. I used the Creality K2 Pro for printing the parts, which easily handle that. Also there is one part, the X-axis plate, which is 300 mm long. So we need a 3D printer with at least 300 by 300 mm working area in order to print that part. I will think about a solution for people that have smaller 3D printers, like splitting the part in two pieces and then connecting them somehow together. The Creality K2 Pro did an amazing job printing this part in carbon fiber PLA with 40% infill and 5 volts without any warping. I mean, just take a look at it, it's a pure beauty. Shout out to Creality for providing me this excellent 3D printer. The Creality K2 Pro is actually one of the best 3D printers I have ever used. You can simply throw anything at it, whether it's a small part or as big as 300 by 300 mm, and it will get the job done perfectly. It's capable of doing anything you would ever need from a 3D printer. It has outstanding print quality, it's fast, it can print in any material with ACE, it can print multicolor, and it has a ton of cool and practical features. I can highly recommend checking out the K2 Pro on the Creality web stores. The links are in the description of the video. Most of the 3D printed parts need some post-processing or cleaning up the support material. Some of them have more support material than usual, but that's because we prioritize the printing orientation of the part to be for getting the most stiffness out of it, as discussed earlier. Here are all of the 3D printed parts, and to be honest, it takes quite some time and filament to make them. I used 40% infill with 5 vol counters and printing speed of 90 mm per second for all of them. If we take a look at this gantry bracket, for example, it took around 7 hours to print, and it weighs almost 250 grams. The biggest part, the X-axis plate, took around 9 hours to print, and it weighs almost 400 grams. So yeah, that's a lot of 3D printing, around 70 hours printing time and around 3 kilograms of filament in total. For printing the X-axis plate, which is 300 mm long, if you have a smaller 3D printer, you can order the part from a 3D printing service. I can highly recommend PCBWay, which along their PCB manufacturing services, they offer 3D printing as well as CNC machining, sheet metal fabrication and injection molding services. You can simply upload the 3D model file and choose your part to be printed in literally any material you want. PLA, ABS, nylon, PPS, and even metals like aluminum or stainless steel, or even titanium. You can choose the color, the infill percentage, and include any other special request that you may have. You get an instant quote for the part, but it's only for reference. After submitting your request, your official quotation will be generated after a manual review by an engineer. PCBWay, being a long-standing supporter of my work, provided a special discount coupon code for my viewers. Check the code in the description of the video. Nevertheless, here are the main components for this CNC build: the aluminum extrusions, the linear rails, the ball screws, and the electronics components. Now I will go step by step and explain how to assemble the CNC router. At the end of this video I will make a cost breakdown, and of course you can find the complete list of all components for this CNC build on the website article. We are starting the assembly by forming the base frame with the aluminum extrusions. We have two 20 by 80 mm extrusions on the sides and three 20 by 40 mm extrusions between them. For connecting them together, there are many types of corner brackets. I decided to use 28 by 28 by 20 mm brackets, as I think they provide the most rigidity. Though we need several of the smaller 20 by 20 mm bracket for some specific locations. For securing them in place we need suitable M5 T-slot nuts, and there are several types of these as well. We need both sliding T-slot nuts and hammerhead T-nuts. The sliding T-slot nuts make a better or stronger connection because they have more contact surface. But the problem with them is that you have to insert them into the aluminum extrusion slot at the face of the extrusion. With the hammerhead T-nuts you can insert them into the extrusion at any place, but they are less reliable because the nut must rotate when fastening the bolt into it, and that sometimes doesn't happen. Anyhow, we need to have the two types, as we always need to add something additionally when the face of the extrusion is already blocked. I prioritized using the sliding T-nuts, but working with them can sometimes be a bit clumsy. We can use two brackets on each corner to make the frame as sturdy as possible. Before fully tightening all the corner brackets, we need to check the squareness of the frame. The easiest way is to measure the diagonals of the frame, and they must be the same. We should also keep an eye on aligning the extrusions at the bottom side. Having a square ruler when assembling this CNC machine is actually helpful. Once we have the base frame ready, all fastened and squared, we can move on with installing the two linear rails on top of the 20 by 80 mm extrusions for the Y-axis. These are HGR 15 linear rails, or heavy-duty linear rails with 15 mm width and height, in combination with suitable HGH CA 15K ridge blocks. For securing them in place, we need M4 bolts with 14 mm length. My intention was to use the sliding T-nuts for that purpose, but at the time of making this CNC I only had M4 hammerhead T-nuts. As I already mentioned, with these hammerhead T-nuts we cannot be sure whether the nut will rotate and properly secure the position. So because of that, I 3D printed some spacers that go into the extrusion slot to fix the T-nuts in a rotated, ready to fasten position. Now if we want our machine to be as accurate as possible, we could check and calibrate the straightness of the linear rails. We can do that with the help of a dial indicator. I used a digital dial indicator that I secured on one of the blocks, and I was measuring the straightness of the rail through the second block that was some distance apart. By sliding the blocks together with the dial indicator, we might find some spots that are misaligned. These misalignments are usually very small. They are measured in hundreds of a millimeter, but we could get rid of them by individually adjusting the rail at these spots. With the same procedure, we can install the linear rail on the other side. The distance between the inner sides of the block should be 586 millimeters. Again, if we want our machine to be as accurate as possible, we should use a dial indicator to make sure that the two linear rails are properly aligned. For that purpose, I used a 600 millimeters long aluminum extrusion, which I secured on one of the rail blocks with the help of a 3D printed bracket, and on the other side I mounted the dial indicator to touch the block on the other rail. Now we can slide the two blocks simultaneously and measure the misalignment between the two rails. This step is actually very important because you see, compared to the previous calibration of the straightness of the individual rails, here we can notice greater misalignment when moving the blocks from one to the other end of the rails. That's so because we are using M4 bolts for securing the rails to the aluminum extrusions, whose slots are 6 mm wide. We should go step by step and align the rails at each bolt location. Once we have the two Y-axis linear rails aligned, we can move on with installing the ball screw for them. These are SFU 1605 ball screws with 16 mm diameter and 5 mm lead. To make the ball screw functional, we need two bearing blocks on which the ball screw will rotate, a ball screw nut mount which will transfer the motion to the gantry, and a stepper motor mount. I decided to have all these parts 3D printed, although there exist suitable prefabricated components for these types of ball screws. I already discussed why I chose to 3D print them. They have specific dimensions that didn't fit my design. By 3D printing them, I had the freedom to make their shape more complex in order to make the whole system as rigid as possible. If we take a look at the ball screw nut mount, for example, we can see its complex shape that has 12 points or holes for connecting it to the gantry. This part actually transfers the motion of the ball screw to the gantry, which means it's one of the most important parts that affect the CNC machine performance. Before inserting the ball screw nut into the nut mount, first we need to insert two M5 bolts into the slots of the 3D printed parts, which will be later used for connecting the nut mount to the gantry. Depending on how big your 3D printer made this hole, inserting the mount into the ball screw nut might be, and actually should be, a tight fit. My recommendation for the printing orientation of this part is to have the hole printed along the Z-axis, which makes it harder for the 3D printer to print the hole 100% round, and that's why the fit might be tighter. Of course, we can always use some sandpaper to smooth some imperfections in the layers and enlarge this hole, because if it's too tight, we risk breaking the part. For securing the nut mount to the ball screw nut, we are using 6 M5 bolts with 16 mm length and M5 nylon insert lock nuts. Next, we can install the fixed bearing block. This is an essential part for the performance of the machine, so therefore I decided to use angular contact bearings instead of our radial bearings that are usually used in the budget prefabricated BK12 blocks. I will be using a pair of angular contact bearings so that they can efficiently accept axial forces that occur on the ball screw. These bearings are bought as a pair and need to be installed according to the marks on the outer ring in order to work properly and accept axial forces. When inserting the bearings into the blocks, we need to have an interference fit or tight fit in order to avoid backlash introduction as much as possible. In such a case, we need to use some force to insert the bearing in place, but we must be careful not to damage the bearing. I printed this simple cylinder shape so that I can hit the bearing on the outer ring where the interference happens. A shim or a distance ring goes between the two bearings. Once the two bearings are installed, we can insert the ball screw through them. First, we insert a 5mm distance ring, and then the ball screw should go into the bearings. But I had a little problem with it. The ball screw shaft couldn't go through the inner ring of the bearings. I tried to use a little bit of force on the outer ring, although the interference now was in the inside ring, but I thought it's safe to hit it few times gently and the shaft would go in, but it didn't happen. That little bit of force I planned turned out to be a bit more force because I was a little annoyed when I was doing that, and so the bearing broke. Now I had to take out the bearing block altogether, which was really hard as everything was tight fit. So I used again some force and managed to get it out. I'm telling you this story of mine so that you know what the catch is if it happens to you. I initially thought that the problem was with the bearings, but then I realized that the problem was with the shaft of the ball screws. When I compared it to the other ball screws, the bearing was going into them without any problem, as a loose fit. I checked the dimension of the shaft with a micrometer and it was 11.996 millimeters compared to the 11.976 millimeters on the other ball screw. That's a difference of only 0.02 of a millimeter, but enough so that it cannot fit in. The problem is that I tried to keep the budget for this CNC machine as low as possible, so these are cheap ball screws, not branded like Highwind or similar, which are at least 5 times more expensive. Again, I am telling you this story in case you find yourself in similar situations, so you know how to solve the problem. Those extra 0.02 of a millimeter can be easily removed with just a fine sandpaper and a screwdriver. I placed the other side of the ball screw onto the bearing block so that I can easily rotate the ball screw with the screwdriver. Now we can simply hold the sandpaper onto the spot while the ball screw is rotating, and after a couple of minutes we will have those 0.02 of a millimeter removed. Now I reprinted the block with 2 slots on the back side, a space which I could use for removing the bearings from the blocks if needed. Please note that I recommend using sealed bearings, as those that I installed are not fully sealed, which is not a good situation because we will use them in an environment where a lot of dust will be generated. Anyhow, now after the 5mm distance ring, I finally inserted the ball screw in place. On the other side, we use one more 5mm distance ring, and we can secure the block bearing to the ball screw with an M12 lock nut. Please note that this is a specific M12 nut with 1mm pitch instead of a standard 1.75mm pitch. This is actually a specific bearing lock nut, which is usually used in combination with a lock washer, but such a combo is not suited in this case as the shaft is not slotted. To make sure the nut won't come loose, I installed one more nut. I 3D printed a custom wrench so I can tighten them. By tightening them, we are actually preloading the bearings because the inner rings of the two bearings are not touching to each other, as we inserted a distance ring between the outer ring of the bearings. This eliminates the backlash that usually occurs at this location of the CNC machine. However, we should be also careful not to apply too much pressure so the ball screw can still rotate easily. Quick note that we could also use different lock nuts here, like for example the ones that have grab screws for securing them in place. Anyhow, now we also need to secure the bearings from coming out of the block at the outer rings. We will use this 3D printed part for that purpose, which will touch the outer ring only. At the other side of the block, first we need to add some M5 nuts. And then we can secure everything with 4 M5 bolts with 30 mm length. This bearing block assembly is rock solid and I cannot feel any play or backlash in it. Next, we need to install the bearing block on the other side of the ball screw. This block is called a floating block because it won't be constrained axially like the previous block, the fixed block. If both blocks are fixed axially, the ball screw assembly would be over-constrained. Therefore, here we don't have to use an angular contact bearing, rather we can use a radial ball bearing, which is of course cheaper. The ball screw shaft has a slot at the end for inserting a retaining ring for keeping the bearing in place. Alright, so now that we have this ball screw subassembly ready, we can attach it on the aluminum extrusion on the side. The bearing blocks should stay 20 mm from the bottom. The stepper motor mounting bracket should be attached at the fixed bearing block side. The stepper motor that I will be using is NEMA 23, rated at 3 amps with an 8 mm shaft. This stepper motor will be used for every axis of this CNC machine. First, we have to secure the stepper motor to the mounting bracket with some M5 bolts and nuts. Then we can connect the stepper motor with the ball screw with the help of the shaft coupler. This is an 8 mm to 10 mm shaft coupler. Now this whole sub-assembly can be properly positioned onto the extrusion, and we can start securing it in place with some M5 bolts and T-slot nuts. The bearing blocks should sit 20 mm from the bottom, so I am using a 20 mm extrusions to hold them in place while I am tightening the bolts. On the other side, we can insert the T-nuts in place and secure the floating block in place with two 15 mm long M5 bolts. This sub-assembly is almost done because now we just have to check and calibrate the alignment of the ball screw with the linear rails. This time I'm using a lever type dial indicator for that purpose. The goal here is to check whether the front and the back side of the ball screws have the same distance relative to the linear rail blocks. In my case, I could notice a difference of around 0.1 of a millimeter between the two sides. We can align them by adjusting the floating bearing block position. I raised the block a little bit to match the value the dial indicator showed on the other side. The ball screw assembly is now completed, and we can repeat this process on the other side of the machine. Once we have the other side done, we can move on with assembling the gantry of the CNC machine. The gantry structure is a combination of 3D printed parts and 20 by 40 mm aluminum extrusions. I will start by assembling the gantry column first. They are composed of two 20 by 40 mm extrusions with 200 mm length for the vertical one and 100 mm for the horizontal one, connected with 28 mm corner bracket. Now to these aluminum extrusions we need to add this 3D printed bracket that will attach to the linear rail blocks. This 3D printed bracket is crucial for the rigidity of the whole CNC machine, as it connects and transfers the forces acting on the gantry to the y-axis linear rails. That's why I designed it this bulky and with a lot of connection points to the aluminum extrusion. Here, first I'm inserting the bolts to connect it to the vertical extrusion. Like already discussed, the bolts make tight fit with the holes of the 3D printed part. They are making a thread into the part so that they will act as a reinforcement to the 3D printed part. Once we insert and align the T-nuts on the bolts, we can slide the part into the extrusion slots. It's always a bit clumsy working with these T-nuts, but they eventually fit in. We need to make sure these two parts are square and aligned, and then we can tighten the bolts. Next, we need to insert the T-nuts into the horizontal extrusion one by one and tighten these bolts again. We need to carefully insert the T-nuts into the slots and push them into position so we can screw the bolts. We use various lengths of M5 bolts here, and just a reminder that the list of all components needed for this CNC build can be found on the website article. Once we tighten all the bolts, the gantry column is now rock solid. We repeat the same procedure for making the other column. Please note that although these 3D printed brackets look the same, they are different, mirrored or a left and right bracket. Next, we can continue the gantry assembly by attaching the crossbeam to the columns. The crossbeam is composed of two 700 mm long 20 by 40 mm aluminum extrusion and some 3D printed parts for forming a truss structure for increasing strength and minimizing bending of the crossbeam. The crossbeam aluminum extrusions will be connected to the column with some 20 mm corner brackets, as we don't have enough space for the 28 mm one. Before securing them in place, we should add T-nuts into the slots of the extrusions, because their faces will be blocked and we won't be able to add them later, unless they are hammerhead T-nuts type. We need M5 T-nuts at the top side for the truss structure elements and the ball screw bearing blocks, and M4 T-nuts at the front side for the X-axis linear rails, and some M5 T-nuts at the bottom side for the gantry bracket. Actually, for the bottom side, it's better to first insert the M5 bolts in place and then add the T-nuts to them and eventually slide the crossbeam extrusions through them. Please note that inserting these M5 bolts in place is a bit of a pain, as there is not much room for the Allen key. I would suggest getting yourself a ball end Allen keys, as they can operate at an angle. At the time of assembling this component I didn't have one, but I bought ones and I used them later for the rest of the CNC assembly. I mean, the design goal of these parts was getting the most rigidity out of them within the limited space we had to work with. I will try to improve the assembly experience for you by adding some chamfers at those locations in the 3D models. Anyhow, now we can tighten both the corner brackets and the 3D printed bracket to the crossbeam extrusion. Before and while doing that, we should always check the squareness of the assembly. This connection between the crossbeam and the column is already plenty strong with the two corner brackets and the 3 bolts connecting the 3D printed parts with it. But of course, now we need to add the other aluminum extrusion on the top side, and in combination with the 3D printed parts that form the truss structure and the ball screw block to complete the crossbeam and the gantry itself. We can see how the ball screw will be positioned, and we can also take a look at the X-axis plate. We can notice that the ball nut mounting block is integrated with the X-axis plate as one part. Because of that, we need to install the X-axis plate to the ball screw nut first. But before we insert the nut in place, we should insert an M4 nut at the back of the plate, as we won't have access later to it. The parts are secured in place with 6 M5 bolts of 16 mm length. I mean, having the X-axis plate and the ball nut mounting block integrated is not an ideal design, especially for the assembly experience, but I had to do it so because of the constraints that I had, because I was trying to make everything out of standard components, as well as to be as compact as possible and rigid as possible. Anyhow, next we can install the ball screw bearing blocks for the X-axis. Their working principle and the assembly process are the same as for the Y-axis. One is fixed block that accommodates the two angular contact bearings, and the other is the floating block with a single radial ball bearing. You see, each block has a unique design that will integrate with the crossbeam seamlessly, providing both structural strength and functionality. That's why I chose to 3D print them instead of buying those standard BK12 and BF12 bearing blocks. Once we have the X-axis ball screw sub-assembly ready, we can install it on the crossbeam aluminum extrusion. In order to do that, first we need to insert all T-nuts in the top extrusion and install the M5 bolts on the bearing blocks. You see me struggling again with inserting all these bolts because of the tight space and the fact that the holes are tight fit. I already discussed why I chose to make them tight fit, to provide better connection between the two bolted parts. Anyhow, I went to my local hardware store and bought myself a new set of Allen keys with ball ends. With this type of Allen keys, we can approach and screw the bolts at an angle, which makes the assembly process easier. And as I already said, I will add a little chamfer to the edges that will further improve the assembly experience. Now we can secure the ball screw sub-assembly to the bottom crossbeam aluminum extrusion. Once we have that done, we can install the truss structure elements. Here I noticed that there was a little gap between the last element and the floating block. And that's so because I haven't installed the bearing in a proper position as in the design. The bearing should be positioned 3 mm into the block. Printed a 3 mm distance ring and positioned the bearing properly. Now we have a perfect fit of the truss structure elements between the two bearing blocks. We secure them in place with some 16 mm long M5 bolts. Next we can add the top crossbeam extrusion and bolt all the elements to it as well. However, we can notice that we don't have access to secure the corner brackets at the fixed bearing block side. We will have to unscrew and take out the whole ball screw sub-assembly in order to secure those corner brackets. But before we do that, we should secure the truss structural elements in position to the top extrusion. So once we unscrew and take out the ball screw sub-assembly, we will have access to secure those corner brackets. And once we secure them in place, we can put back the ball screw sub-assembly. It's still a bit of a pain to secure the bearing blocks because of the tight space and that the T-nuts can move around easily. I had to remove the truss structure element next to the fixed bearing block in order to have better access to position the T-nuts in place so I can screw the bolts properly. I must admit that this is not the smoothest assembly experience, but I have said this several times already. My main goal was to make the machine as rigid as possible. I mean, just take a look at how rock solid this gantry turned out. It deflects only 0.03 of a millimeter at the center with a force of around 50 newtons applied on the top, or 0.06 of a millimeter at 100 newtons of force. Just for a reference, a single extrusion had a deflection of around 0.45 millimeters at the force of 50 newtons. So that's around 50 times increase of sturdiness. Next we can install the X-axis stepper motor. In a similar fashion to the Y-axis stepper motor, we secure it to the mounting bracket with some M5 bolts and nuts, and then with some T-slot nuts secure it to the vertical extrusion of the gantry at a position to couple with the ball screw. Once we have the stepper motor installed, we can move on with installing the X-axis linear rails. On the bottom extrusion I inserted the slide T-nuts, but I forgot to do that for the top one. So I will use hammerhead T-nuts there with some 3D printed spacers between them to make sure the T-nuts will stay correctly in position when I screw the bolts. The installation process is the same as the Y-axis rails. The rails should be positioned in the middle of the gantry or 70 mm from the outside of the vertical extrusion, and the distance between the two rails should be 90 mm. Using a dial indicator we can fine-tune the distance or the alignment between the two rails. We should also check the alignment of the ball screw and the linear rails along the Y-axis, and if needed adjust the floating bearing block position. Once we are done with the fine-tuning, we can secure the linear rail blocks to the X-axis plate. Actually, before we do that, there are a few nuts that we should insert on the back side of the X-axis, because we won't have access to them when the rail blocks will be in place. These are M4 nuts that will be later used for securing the Z-axis rails. Now we can secure the X-axis plate to the 4 rail blocks with some 14 mm long M4 bolts. This completes the x-axis, and if we take a look at the gantry deflection now, we can notice it further improved because of the ball screw and the X plate. At a force of around 50 newtons there is only 0.02 of a millimeter deflection, or at a force of around 100 newtons only 0.04 of a millimeter deflection. Anyhow, now we are ready for the marriage or connecting the gantry or the x-axis sub-assembly to the y-axis linear rails. First, we can secure one side of the gantry to the linear rail blocks with some 20 mm long M4 bolts. Again, we have a little bit of struggle screwing some of these bolts because of the tight space. Once we secure one side, we might come to a problem on the other side, or the 3D printed bracket holes might not align with the linear rail blocks. This might happen if the gantry is not perfectly square or the distance between the two linear rails is not right. In my case it was something else. The gantry crossbeam aluminum extrusions were around 1.5 mm longer than the extrusions at the base frame. So that's something that you should consider when building this CNC machine and check them before you start assembling them. Luckily I had enough space to compensate for that by moving the y-axis linear rails further outside. I loosened both rails and connected the second gantry side bracket to the rail blocks so that it gives me the proper distance that the two linear rails should have according to the gantry size. Now that I loosened the rails, I wanted to fine-tune the distance between the two with the dial indicator again. I had to print another bracket that would hold the 600 mm extrusion and secured it on one side of the gantry. On the other side, again I placed the dial indicator to touch the rail block and then I played a little bit with it. Once we are done with the fine-tuning, we could move on with connecting the gantry to the y-axis ball screw nut blocks. However, here we might face again a problem of not fitting with each other. In this case, the solution is adjusting the ball screw height. I loosened the bearing block and slightly lowered it and secured it again. I mean, these problems occur because we don't have fixed position of the holes for assembling and connecting the sub-assemblies to each other. Rather, we have the aluminum extrusion slots, which are wider than the bolts. Anyhow, once we align the bracket and the ball screw nut block, we can secure them from the top side with two 50 mm long M5 bolts, and from the bottom side with two 70 mm long M5 bolts to the aluminum extrusions with tin nuts. We additionally secure this connection with some 12 mm long M5 bolts. When securing the other side of the gantry to the ball screw block nut, in order to make the CNC machine square, we should measure and position both sides at the same distance from a reference point. Once we have both ends of the gantry secured to the ball screw nut blocks, we should again fine-tune their position by rotating the ball screw by hand to make sure the machine comes out square. Alright, so now we can move on with assembling the Z-axis. We're using the same HGR15 linear rails for the Z-axis as well, but they are just 300 mm long. They will be secured directly to the 3D printed X-axis plate, and for that purpose first we need to install the M4 nuts on the back side of the plate. These rails go vertically, so we should be careful not to let the blocks fall off of them. I used a hand clamp to prevent that. For securing the rails in place, we need some 25 mm long bolts for the top three holes, one 16 mm long for the hole behind the ball screw nut, and 20 mm long for the holes behind the X-axis rail blocks. The distance between the two rails should be 87 mm, and we can fine-tune them by using dial indicator like we did for the other axis. Next is the Z-axis plate that should go on the linear rail blocks, but because here we also have the ball screw nut block integrated with the Z-axis, We have to make the ball screw subassembly first and then attach everything to the X-axis plate. I had a tight fit between the ball screw nut and the block, so I used some clamps to fit in place. Though we should be careful in such a situation, as we might break or delayer the 3D printed part if too much force is applied. We can always easily sand a little bit the hole to make the fit a bit looser. The bearing block assembly is the same as the previous one, though you might notice here that I used radial ball bearing instead of an angular contact bearing, and that's so because I didn't have the angular contact bearings at the time of making the machine. Of course, it's better to use the angular contact bearings to get better accuracy of the CNC machine. At the back side of the plate we need to insert 6 M5 nuts that will be used for securing the router mount, and also pre-install all the bolts that will be used for securing this sub-assembly to the rail blocks and the X-axis plate. Though when I was writing this part of the script and going through this footage, I couldn't believe my eyes that I've actually forgotten to secure the ball screw nut to the block with the 6 M5 bolts. I have checked the machine to see if that's true, and it was. I've been using the machine all of this time. I made all these demo examples without these two crucial components secured. I guess I was lucky because I really had a tight fit between them, so it didn't affect the performance of the machine too much. Anyhow, now we can install the Z-axis ball screw sub-assembly in place. The bearing blocks are secured to the X-axis plate and the Z-axis plate to the linear rail blocks. Then we couple the stepper motor with the ball screw through the mount bracket that is secured with 4 M5 bolts at the top of the X-axis plate. Now we are almost done with this CNC build, and what's left to do now is to install the router in place. I decided to use probably the most popular and available router for DIY CNCs, the Makita RT0701C. I designed a mount for this Makita router that has 65mm diameter. The mount is secured to the Z-axis plate with 6 M5 bolts. We can notice here how the 3D printed parts can break or delayer when significant force is used on locations that have thin material or wall. I modified and reprinted this part with larger walls around the holes. Now it was strong enough to be properly bolted in place. Lastly, we can simply slide the router into the mount and secure it in place with the 3 M5 bolts and nuts at the front of the mount. And that's it, we are finally done with this CNC build, or at least with the mechanical part of it. However, as this video is already way too long, I decided to split up this CNC build guide and explain the electronics and how to make the wiring and the control box of the CNC machine, as well as how to set up the machine and do your first cuts with it in my next video. Real quick, this CNC machine is based on Arduino and Gerbil. I used an Arduino Uno in combination with a CNC shield for easily connecting everything, and for driving the NEMA 23 stepper motors, I used DM542 stepper drivers. The motion control firmware is Gerbil, and for setting up and controlling the machine and sending G-codes to it, I used the Universal G-code sender. They're both open source. I mean, it doesn't have to be Arduino and Gerbil. We could use any other CNC controller with this CNC build, like for example Linux CNC, Gerbil Hall, Mach 3 or 4 and others. This Arduino and Gerbil combo is the simplest and cheapest option for a CNC controller, but of course it lacks some advanced features like real-time control, backlash compensation and better configurability. If you are not comfortable making the control box on your own, there are also ready-to-use CNC control boxes, even with the cables for the stepper motors included. Anyhow, for a detailed guide on how I built the control box for this 3D printed CNC router and how to set up the Gerbil and control the machine, check out the next video. There will be also a separate video where I will show you how to make the baseboard and the dash shoe for this CNC machine, as well as how to get started, set up the machine and make your first cuts with the CNC machine, and how I made these demo projects that we are seeing here. Before we end this video, I would like to show you a few more things, or how rigid and accurate this machine turned out and how much it costs to build it. For demonstrating the rigidity of the CNC machine, I inserted a 6mm shaft on the router, and using a dial indicator, I will measure how much the machine will deflect when a load is applied. First, I am testing the x-axis rigidity. At a force of around 50 newtons, the end mill deflects around 0.16mm, or 0.24mm at a force of 70 newtons. On the other hand, the deflection in the y-axis was around 0.22mm at a force of 50 newtons, or around 0.32mm at a force of 70 newtons. That's a little bit worse result, but it was expected as this is a gantry style CNC machine which usually has less rigidity in the y-axis compared to the x-axis. As for the z-axis rigidity, I measured around 0.18mm deflection at a force of 50 newtons and 0.25mm at a force of 70 newtons. This rigidity of the CNC router resulted in accuracy within 0.06mm when cutting aluminum using appropriate fits and speeds. I made this test part out of aluminum with the following settings. For the roughing, 4mm depth of cut, 1.2mm width of cut, and 1200mm per minute feed rate. The offset was 0.3mm. Then for the final contour pass, 2mm depth of cut with 500mm per minute feed rate. I measured the part with a micrometer and all the shapes in all directions were within 0.06mm accuracy. I will say it again, I think that's a pretty decent result considering it's a fully 3D printed CNC router using a trimmer router and an Arduino and Gerbil for the motion control. As for the cost, at this point, without the electronics, you will need around $700 to $900 to build this CNC machine. Of course, this very much depends on the source where you will get the parts from. You can find the complete list of all components needed for this CNC build, including suggested links for each part, on the website article. The link is in the video description. Also, as mentioned earlier, you can easily scale this CNC build and get larger working area by choosing the appropriate parts. All these details will be included on the website article. Nevertheless, stay tuned as more CNC related videos are coming. I will also make a Discord or something similar for everyone to share their experience building this CNC machine and make a community around it for solving problems and improving the machine. I hope you enjoyed this video and learned something new. Don't forget to subscribe, and for more tutorials and projects, visit howtomechatronics.com.